Hey, chemistry friends, I'm going to take a few minutes and walk you through some examples of the VSEPR theory. Now, VSEPR is referred to as valence shell electron pair repulsion theory. Honestly, I don't really care if you remember that acronym. What I do care is that when we do covalent compounds, you need to realize that these electrons want to orient themselves far apart as possible from other electrons so that it can make the correct molecular shape. So ultimately, we're making molecular compounds. So here we go. First off, when to use VSEPR? VSEPR we use to form Lewis structures of covalent compounds. It's really important. Covalent compounds are those made of two nonmetals or more. Let me scoot myself up here there. Okay. It's also when we share electrons, where ionic compounds is when there's a give and take of electrons, and it's more so taking of electrons. Covalent's more of a sharing of electrons. And the most important thing is it's two nonmetals. So it's actually the upper right-hand corner of the periodic table. And so we want to remember, though, a Lewis structure. And if you recall down here in the lower left-hand corner here, you'll see this Lewis structure. And we did these for just a simple compound where we just show the number of valence electrons. We're going to do a Lewis structure for an entire molecule now. Don't worry, hang in there. Okay, next slide. Sorry. All right. First off, why are we going to use VSEPR? First off, we have to think about the valence shell. What are the outermost electrons doing? Those are the electrons that's going to go and do their job. It's kind of like the worker bees of the hive. That's the ones that's going to do the job. The inner electrons are kind of the drones just hanging out, and the nucleus is like the queen bee. Also, electron pair. So electron pair is part of the term VSEPR, and we remember there's two electrons that can be in each lobe of every orbital. If you recall, when we drew our orbital diagrams and we drew one box for S, 3 boxes for P, 5 boxes for D, we were showing how many lobes are there that can actually hold 2 electrons in each lobe. And again, the repulsion comes from with VSEPR as to these electrons want to stay far apart from each other because we know like charges repel, so they don't want to be anywhere near each other. So our goal in chemistry 1 is we need to be able to draw the Lewis structure of a covalent molecule. We need to determine the hybridization of the central atom. We'll get there in a minute. We need to determine the molecular geometry of the molecule, and then we need to build it with a modeling kit. Now, I have modeling kits at school. You may not have some. You know what? I've built tons of models with toothpicks, marshmallows, gumdrops, all that good stuff. Whatever you have on hand. I was even considering building it with some popcorn tonight because I did not have any marshmallows or gumdrops. So really, you can use about anything. However, I do want you guys to know there is a lot more to VSEPR. I don't want you to think this is the only thing ever, but in chemistry 1, this is all we need to go. If you go into AP chemistry or if you choose to take some chemistry in college, you're going to take this a lot farther, okay? So before beginning, let's think about bonds because we're going to start to form single, double, and triple bonds. So a single bond is when we have a sharing of just 2 electrons. The single bond, it's not the strongest bond of all, and it's the longest bond of these 3 electrons. Of these 3 bonds, single, double, and triple. So the double bond is a sharing of 4 electrons. It is stronger than single, but it's shorter than single bonds. And finally, triple bonds are the sharing of 6 electrons. It's the strongest of 3, but yet the shortest of the 3. So I like to think of this as this first one. A single bond is like when you're talking to somebody and there's not like a huge commitment right there. It's very simple to say, hey, I don't really want to hang out with you anymore, and that bond can be broken. A double bond is more so like you're engaged. So you haven't totally tied the knot yet, but you're very committed to each other. So therefore, it is more difficult to break a double bond than it is to break a single bond. And it's stronger and it's a shorter bond. So meaning that they're closer together than the people who are just talking. And finally, the triple bond, I think of it as like a just married type of bond, where that bond, it's the strongest of the 3. So it's very hard to break. And it's the shortest of the 3, meaning that they're very, very close together. So it's just a silly way to help me remember how single, double, and triple bonds work. Now, the steps for drawing the Lewis structure of a molecule are listed below, and I'm going to go through each step and just take you through on how to work each step. But if you want to see all the steps in one place, this is a great stopping point on your slide to take a look at. So we're going to go through each step, and let me start this with number 1. First off, we're going to determine the total number of valence electrons for the molecule. And here's our example molecule. We're given H2CO. Now, to determine the total number of valence electrons, we have to first think, okay, carbon has 4 valence electrons. There's only 1 carbon in this molecule. Oxygen has 6 valence electrons. There's only 1 oxygen in this molecule. And hydrogen has 1 valence electron. And again, there's 2 hydrogens, so we have to count that 1 valence electron twice, for a total of 12 valence electrons. Now, ideally, you guys, we want to get an even number. If we get an odd number, something's up and something we didn't calculate something correctly at this point. So step 2, we're going to identify the anchor or central atom. Now, we want to find the least electronegative. So one thing to point out, neither hydrogen nor fluorine can ever be a central atom. The reason is fluorine is super duper electronegative, and hydrogen can't hold more than 2 electrons anyway, so it can only have 1 bond. Another example, the central atom usually appears just once in the formula. So if you have PF3, notice there's 3 fluorines, so that's going to be really hard for a fluorine to be a central atom. It's not always the case, but that's a pretty good indication. And number 3, if there are 2 atoms that could be the central atom, the lower electronegativity will be the central atom. So we have to think back to our periodic trends. With the highest electronegativity is fluorine. So the further away we get from fluorine, that's the lower electronegativity. So that's why carbon is a really common central atom. So we've identified the central atom here, in this case, as carbon, because carbon is less electronegative than oxygen. So hydrogen's not even an option to be the central atom. Now we're going to draw the skeleton structure. What that means is we're going to draw these bonded things with just a single line representing a shared pair of bonding electrons. So what I want you to see here is that this bond between carbon and oxygen actually indicates 2 electrons. It indicates 2 electrons for oxygen and 2 electrons for carbon. This bond here between hydrogen and carbon indicate 2 more electrons. So carbon has 2 more electrons, hydrogen has 2 electrons. And here we have carbon with hydrogen. Again, that line indicates 2 electrons. So each line or each bond indicates 2 electrons. So therefore, a double bond will indicate 4 electrons, a triple bond will indicate 6. So it only shows, the skeleton structure shows how the atoms are linked together. And we had to figure out the central atom, which is carbon in this case. The next thing we do is be sure each atom fills the octet rule. So we want to get 8 electrons. So, 8 electrons except for hydrogen, because remember, hydrogen can only carry 2 electrons. Only has room for 2 electrons. That's what we're missing over here. And that's because of the 1s orbital. Let me pull this down here. Okay, so what we have here are these lone pairs now. So now we want to do the octet rule, and we said, okay, with oxygen, this bond counts for 2, so we're going to add 4, 6, 8. So the oxygen has access to 8 electrons. Here's our carbon. Carbon, this bond counts as 2. This bond counts as 2. This bond counts as 2. That's 6, but we need another shared pair or a lone pair on that carbon. So therefore, we're filling the octet rule. It doesn't matter that carbon doesn't have 8 electrons. What does matter is we're trying to get that goal of the initial number of electrons we added in the first place. So we realize we count the number of electrons on our Lewis structure. So let me count this total and just show you. We have 2, 4, 6, 8, 10, 12, and 14. So we have 14 electrons total in our Lewis structure right now. However, we only need 12. If you recall, 12 is our valence number of electrons. So what we do is if there's too many electrons, like we have in this case, we make double and triple bonds. However, if there are not enough, which is not this case, we can add lone pairs to the central atom only. You can't just randomly add lone pairs to other things. So what we have here is we're going to make a double bond between carbon and oxygen. Because we're making that double bond, you're going to see that this oxygen now has only 2 pair of electrons because we have 2, 4, 6, and 8. And then carbon now has 2, 4, 6, and 8. We want to determine the hybridization of the central atom. So we want to see now how many things are attached. Hybridization is just how the s and the p orbitals overlap. And so that's a whole nother thing in chemistry. So at this point, just kind of trust me on the fact that hybridization, if you have one thing attached, it's an s hybridization. If you have 2 things attached, it's an sp hybridization. 3 things is an sp2. 4 things is sp3. 5 things is sp3d because that's 1, 2, 3, 4, 5 things, and sp3d2 is 6. So what we want to look at here is our carbon, and we have a hydrogen attached, and an oxygen attached. So therefore, we have 3 things attached. That means our hybridization for this molecule is going to be an sp2. The reason why we want to know that is so now we can figure out our molecular geometry. So we're going to use this handy dandy little guide to determine our molecular geometry. And the way that we do this is we know it's an sp3. So we're going to focus on 2 columns in particular. This column with the hybridization and this column with the molecular shape. The picture is also going to be very helpful. So we're going to look at sp3, and we know based on our structure that we don't have any lone pairs on carbons, or I'm sorry, sp2. We don't have any lone pairs on the carbon, but we have 3 actual bonds attached. So therefore, we're going to have sp2 hybridization, and we'll have a trigonal planar, will be our molecular shape. This shape right here on the screen is a trigonal planar. It's trigonal because it's triangular shaped, and it's planar because it's flat. Think about a plane in geometry. A plane in geometry is a flat surface. Now, I want you to take a minute and try some more. So I want you to try these following right here and see if you can determine all the steps. You may want to write these down, go back to the original steps, and just walk through it so you can go through each one. Pause the video after you do that, and on the next slide, I do have the answers to this. So go ahead and pause your video so you can take a look at these in particular. And let's go on to the next slide, and so you'll see the answers. So you can check yourself. I put on here the number of valence electrons for each molecule, the hybridization, and the molecular geometry. So hopefully you guys, this can help you a little bit. We're going to do lots of practice in class. And remember, I don't expect you to memorize that table that we can use with the hybridization and the molecular geometry and shape. You just have to be able to use it. That's what I'm concerned about, is that you guys can actually work through this and use the information that I'm giving you. Hang in there. I'll see you soon.